Proverbs. It's about time.
Oh, that's a good one. See, that's a good one. I like that one. Very little thinking.
You know,
Just gets it.
That was
Get it.
classy. That was nice.
Do another.
Very mindful.
Did you like your Thanksgiving?
Aww. All right, announcements. We've already talked about some of these, but we have just enough time before the end of the quarter to squeeze in one more chapter test, which is on oscillation. So we've got our second to last lesson today, our last lesson for the quarter and thus the semester on Thursday. Next week, though, it starts our exam week. So I did post in rooms a couple weeks ago about the schedule. So it's Monday and Tuesday, take a break on Wednesday because it's Wellness Wednesday, so we got shorter classes, so no exams next Wednesday, and then Thursday and Friday they'll pick that back up. And then the week after that is the last week right before Christmas break, which is when our egg drop project is due. I will give you one full class period to work on it, and then of course it will be due either that Wednesday or Thursday, whichever one is the 8A, I think it's Wednesday. So that is the plan. So there's not a whole lot of time left, but there's still a bunch of points left up for grabs. Of course, there's the pods and the quiz from the lesson last class. There's this class, there's next class. So there's 3 pods, 3 quizzes. There's a review guide, which of course is an optional quiz grade. There's the chapter test on oscillations that we'll take. There's the egg drop project, which is another test grade. And the semester exam, which technically doesn't have to count for the second 9 weeks. However, if you score well enough on it that it helps your grade, I can put that in as another test grade too. Okay, so lots of points up for grabs during these last 2.5 weeks of the semester. Okay, so in terms of studying for the semester exam, I don't have a particular review guide for you. However, all of our past tests should be open, so you can go and click on that testing link that you can find in Teams, or if you have extended time, it's in your email. And you can see all of the test questions, the ones that you got right, as well as the ones that you got wrong. And that is the best way to study for the exam, okay? Because practice makes better. Perfect.
Are you allowed to use a team test on the semester exam?
No. Sorry. Sina.
I use a what?
Oh, my brain went smooth. Keep going.
Okay.
Hold on.
The egg drop?
He's
Why?
talking about using your 50 team points if and when you get up to that many to take a team test. Like, does that count? Can you take a team test for the semester exam? And I said no.
Aww.
That's only for the chapter test.
We only have 15.
Yes. Damn, that's
Okay,
huge.
so when's the egg drop?
Egg drop is going to be that Wednesday or Thursday of Christmas break, or before Christmas break. So exactly in 2 weeks, Wednesday or Thursday.
So you're just supposed to thug it out, just like make something?
Make something?
Your egg's supposed to survive.
If you
It's
haven't
not going
looked at the specs on the Egg Drop project, I did post
Yeah, that was a
in
while ago.
rooms maybe 3 weeks ago or so. And there's a file, so make sure that you read the file. There's lots of things that you cannot use.
I'm using
So
bubble wrap.
pay close attention to that. If you have a question, please let me know. But I've put as many things on there as I can think of. So hopefully you should have already been thinking, designing, maybe getting supplies, and maybe building your egg drop project. If not, so there's still time before that Monday or Tuesday. I think. Hold on. Let me double check.
Might as well start now.
I think
It's on my mind.
I think it's on the Monday, Wednesday, Friday.
I already have something on mine.
Like, all I saw was an egg wrapped in bubble
No,
wrap.
so
That's all I
it is
had.
our Tuesday, Thursday. So
No wonder why I felt
we're
the
gonna
last one.
have, so the work day is the Tuesday, the 17th, and then the egg drop itself is due on the 19th, that Thursday.
I'm this close.
Alright, any other questions for the good of the order?
Parachute.
Heather? Yes. Oh, speaking of, if you did not get a chance to pay for the field trip, I don't know, maybe you just don't have rooms open on your devices or not, but I sent you plentiful messages over the weekend, including yesterday. That yesterday was the last day to pay. It's still open. Not by design, but lucky for the people who forgot to pay yesterday, it is still open today. Hopefully we can close that out for tomorrow. But the people who paid late, as in on the second bus, we do have enough students that there will be a second bus. We may not get shirts, but we'll all be able to go. But the more people who pay, the fuller that bus becomes, the more likely that we will actually get shirts as well. Okay, so if you didn't pay before, you can still pay today, assuming that you are eligible. Huh?
Are you saying shirts or insurance?
Shirts.
We're gonna get insurance.
Oh, no, I thought it was for the bus.
Like, why do we need insurance?
No.
Because what if something
I mean,
happens?
you need insurance, but
Yeah.
like,
Yeah.
When do you think y'all will be back? Like from
Like the time that we're coming back to Paxton after the field trip, around 11.
PM
Yes.
at night? When
That's
it's
what
dark
that
out, when it's dark outside?
Yes, when it's
How
dark.
long's the drive?
3.5 hours.
Oh.
That
That's
makes
Tampa.
sense right there.
It's on a bus with their friends.
to actually go visit my
Oh, I'm
cousin.
finna take
Well.
some best nap if I go.
Yeah.
So,
Oh, you better bring some fucking
5:30.
brand by me, or like some
So we'll get there right before 10
because
when it opens, and we'll be there from 10 to 6.
See, it's about who you
So
sit
8 hours
with.
inside.
I might not go.
So I'm gonna use the little person as a pillow.
Well,
Well, I
I need
can't go.
coasters, and you do
Why?
have a lab to do as
I
well.
have a competition the day after, and
I'm paying money for a lab.
it's sparse. It's crap. So if I get back here at
You would have a
11,
lab if
and
you
I
stay
could probably still
at
get my hair done, and then my lashes done, and then all the other stuff tied together. And I probably have practice the night before that we leave. So like, ain't nobody going out with y'all.
Is it like kind of like?
And I actually got the
have
thing
some
for it.
exercise
Look,
right on my table. Alright, so
83.
one more thing about the trip, again,
I use the other one.
I took notes so I could get credit.
Today is the due last day to pay. You can pay online and then you can give me the permission slip later. That is perfectly fine. But if you are even possibility thinking of going, you gotta pay today. Just remember you need to be eligible to go, so you needed to have a C or better from the first 9 weeks, or for the progress reports during the second quarter. Okay? Cool. Alright, I think that's all of my announcements. Let's get into more oscillations, simple harmonic motion. We've got our mass on a spring here. We can see that's oscillating. We also have our pendulum. Bob has come back to play with us. So we will take a closer look at both of these cases as we dive deeper into the topic of simple harmonic motion. In your data book notes here, we have. Where do you want to go? Because I was working on
I heard exams, I got scared.
Can I get a new sheet thing? Because I don't know what happened to mine.
I have a spare.
An equation booklet?
Yes.
Sure.
I lost.
I have 3. I don't know
Notebook for your class.
I ended up in there, bro.
You lost it. If you left it in here,
No,
there's a
that's
good
the
chance
purple
I
one.
stuck it in
You-
the
you're supposed
little
to change
black milk crate down there. That's where I lost it. Okay, so as we can see, we are still in the C chapter, C1, and at the top of the page, look at that. So we've already seen 3 of these 4 equations, so we are going to take a look at the first one today. So for anything that oscillates with simple harmonic motion, it's going to go with this particular equation. Now, not all things oscillate, or not everything that oscillates has simple harmonic motion. So we'll kind of get to why that is here in just a minute. So the equation for simple harmonic motion has to follow the acceleration is equal to negative omega squared times x. Of course, x is our position, and these are, so the direction's important because they're both vectors, and then the omega, remember that was angular frequency, because we're talking about oscillations and not just circular motion now. So, for something to say that it's simple harmonic motion, it must follow this rule. As in, if I were to look at a situation, the forces acting on it have to cause an acceleration that goes by this equation. So we're going to take a look and see, does the mass on a spring and does the pendulum exhibit simple harmonic motion? We're going to kind of prove those on our board today. So here we go. So let's take our mass on a spring, and it doesn't matter if it's an up and down spring or a left and right spring, we approach it the same exact way. So recall that we have a mass on a spring. This is a smooth surface, so there's no friction, and it's at rest, so we're going to track the equilibrium point like so. So I'm going to stretch it out. As I stretch it out, there's a displacement x. That's our that's the expansion or compression of the spring, and that's also going to be the maximum displacement, which we call the amplitude. And so we're going to let it go, and it's going to oscillate back and forth. But as I let it go, or even before I let it go, let's take a look at our forces acting on the mass. Of course, we've got our force of gravity pointing down and the normal force, but those forces don't really matter because we're looking at the acceleration in the x direction. So I know, because we've talked about spring force before, way back in A2, as I pull the mass to the right, where does the spring force want to point?
Left.
It points left, because the spring force is a restoring force. It wants to get it back to its original equilibrium position. So if I displace it to the right, the spring force has to point to the left. Remember, that's FH, stands for Hooke's law. Way back in A2, remember our Hooke's law equation is negative kx, where again k is our spring constant, x is going to be the displacement of the spring, not the spring length itself, but how much it's been compressed or stretched. So we want to come up with an expression, we want to derive an equation that shows the acceleration of the mass on a spring. So here we go. And we're going to start off with our good old Newton's second law. The acceleration of any object is equal to its net force divided by the mass. And so the net force, we're going to add up all of the forces acting in the x direction. There's only one, the spring force. And well, you know what that is, so I'm going to plug this kx straight into our f net equation here. So negative kx divided by m. And I'm going to rearrange slightly so that it looks like acceleration is equal to negative k over mx. Does this match in form our simple harmonic oscillator equation? Does it look like it?
I don't think so.
No.
Well, almost. So this is the general case for anything involving simple harmonic motion, where the omega is the angular frequency. If we're looking for a particular case, like the mass on a spring, pendulum, something else, then that omega is going to stand for something physical about the situation, okay? So as I compare these two equations, the major things are there. So the acceleration is equal to negative times some number times x. So these do match up, okay? In fact, as we match them up, we can see that omega squared, the angular frequency squared, happens to be equal to the ratio of the spring constant and the mass, specifically when we're talking about mass on a spring. Okay. And what if we're solving for omega? Maybe take a square root here. So omega is equal to the square root of k over m. And remember, there is a relationship, our second equation on our C1 box here, that says that the period of the is equal to 2 pi over the angular frequency. Huh. Okay. Well, if I know that the omega is equal to this, let's plug that in and see what let's see what happens. So 2 pi over the square root of k over m. This is a complex fraction. Once I fix it, I get 2 pi times the square root of m over k. Hey, isn't that the period of oscillation for a mass on a spring that we talked about last class?
Huh?
Yes.
It is.
Is
It
it?
happens to be our third equation in our equation sheet.
Wow.
Did you put M over?
I did. Because I had to fix the complex fraction.
Oh.
Take the top and multiply by the reciprocal of the bottom. So we just derived our period of a mass on a spring equation. Cool. So, because these equations matched up, we can say yes, the mass on a spring does exhibit simple harmonic motion. Now, let's say I'm dribbling a basketball. Okay, this is an oscillating motion. It's repeating. There's a constant rate. I can measure the period or the frequency. So it's oscillating, but does it exhibit simple harmonic motion? We got to look at the forces that are controlling the motion. Okay, in most of the time, as I dribble the ball is in free fall. Okay, as it falls down, as it bounces up, and it falls up. Most of its time is spent in the air with me not touching it and the floor not touching it either. Okay? So most of its motion is being controlled by the force of gravity. But is the force of gravity changing with respect to the position of the ball? No. Okay. Now, if I were dribbling this like a mile up, which would take a really long time for it to fall and then to bounce back up. But let's just play with the idea, okay? Would the force of gravity change then?
Yes.
If I have a really, really big height? Yes, okay? But since I'm dribbling close to the surface of the earth, we're going to assume that the force of gravity is constant because I'm close to the surface. Just like we assume the G is constant as long as we're close to the surface of the earth as well. Okay, so if the force of gravity is constant, as in it's not changing based on the height, the force of gravity cannot produce simple harmonic motion. So although it does oscillate as I dribble the basketball, it is not simple harmonic. Okay, but the mass on a spring does. Let's take a look at the pendulum though. Okay, does the pendulum exhibit simple harmonic motion?
Yeah.
Well, it oscillates, but is it simple harmonic? We're about to find out. Okay, so I'm gonna erase this unless you guys want to take a picture real quick.
Find us next time. Find us next time, on.
Yes.
No,
You're such a poser.
we'll be right
There's
back.
no point.
Yes.
People get 4 years.
Do I want more Legos?
You know,
I
it'd be
will
fun.
always take more Legos.
Magic school bus with physics.
I was gonna say you have a problem.
Magic school bus with physics.
I do have a problem, but it's a good problem.
Watch us smash the bus.
It's not a legal problem. It's not a moral problem. It is a perfectly acceptable addiction.
Right. So,
What are we
do I just get?
Legos.
Do I just
Oh,
get
Legos
you
are
back?
good
Kind of
addiction.
obsessed.
It's
They're
okay.
good addiction.
I don't want to buy you a set that you probably have already had or.
That is an excellent thought.
Get him one of the keychains.
Keychain.
You know the keychains that they sell?
Oh yes, I know.
Do you like the cars?
He knows.
Do I like the
Don't
cars?
worry about
No, not really. So if you notice that all of the Legos on the display, except for the Christmas stuff, that one, they're Star Wars, but two, they're all from the first 3 movies. Okay. So,
Get them the.
and that's kind of on purpose. One, because I can't collect everything.
So true.
Because, I mean, yes, I do have a big room, but as you can see, I filled most, if not all, of my shelf space. I can still squeeze in some more, but I can't collect, you know, things from the prequels or the sequels or the standalones or the movies. Unless it's something that I really, really, really like, I'm just going to stick with the originals. However, I have put on our Mr. Maynard classroom wish list on Amazon. I have some current sets that I don't have that I would like. So if you're looking to buy something for me, which by all means, you absolutely do not have to get me a Christmas gift. But if you are wanting to show your appreciation, there is definitely a good place to start. Or you could just bring in your box of old Legos that you used to play with and you don't want to play with it anymore. You can wrap that up and give it to me, okay? I like that too, because it's always like a fun, like seeing what kind of pieces, what kind of figures are actually in there. So, which is always a fun thing to do, so.
Where's this located?
The Amazon wish list. You can either search for my name on Amazon, or I'm actually about to send out a message about like if you want to get me like food stuff, like treats for Christmas things, because I don't typically eat a lot of the things that I used to. So I'm gonna give you some ideas. Again, and the idea here is not that I'm asking for gifts, but I know that certain students and their parents want to do cool things for the teachers. And sometimes they're goodies, but I don't eat certain goodies, so it would be, it helps for you guys to know. Hi, guys ready? And back.
No, they didn't give us a pass. I was on a field trip like for this.
Yes, I remember seeing it. Cool. Alright. Yeah, so it would be a little embarrassing for you to bring me like a homemade something and I can't eat it. So
Are you allergic to something?
I'm not allergic, but I do
Picky?
stay away from gluten and food colorings. We try to eat as natural as possible. So like no added sugar, no high fructose corn syrup.
Organic.
Organic if possible. I mean, we don't really have the money. Like we would buy like, you know, like grass-fed beef and free-range eggs, but they're expensive.
What's so special about free-range?
So when you eat an animal product or an animal byproduct, its food dictates how good the meat or the eggs taste. So like grass-fed cows, instead of cows that are, you know, kept in a barn and they're fed like corn mash and stuff, grass-fed meat tastes better. The eggs, like if you get free-range eggs or if you actually have chickens and you get eggs, the eggs, especially if they're free-range, if they eat like bugs and insects and stuff and not just like the cornmeal that people usually feed chickens, you'll notice that the yolks are like super like golden and orange and they taste so much better. Butter, like we get butter, it's like Irish butter. And it tastes so much better than the regular, you know, bland store-bought butter, because of what the cows eat. So what the creatures eat will directly affect the nutritional value and the taste of the products that you use. So all that to say, not necessarily that, you know, you want to buy me the pack of grass-fed ground beef. That would be silly. But in terms of like packaged items,
I'll get
we
you a
really
chicken.
don't buy a whole lot of packaged foods. We typically buy, you know, like whole foods, not to be confused with the market. But that my wife is really good at cooking stuff, so we make our own sauces and mayo and things like that. It's my clock up there.
Like, is that every hour?
You did not just
It
pull the
plays a
Nara
different
Smith.
carol every hour on the hour. So
So festive, right?
you guys will always be listening to O Christmas Tree.
You might get a little frustrated throughout the day.
I don't, because
I'll
it
wait
plays a
5
different
minutes after
song
after
each hour.
school just to listen to
So-
I would crash
the other
out.
one.
I don't get bored of this.
Every day I come here and I hear a song
Yeah,
every
no,
hour.
it's fast.
I lose it.
Yeah. And if you stay an extra 5 minutes, you can hear it at 3.
Yeah, my
And
bus
it's
lady-
going to be a different song.
My bus lady's not really good.
I do eat ice cream, but it needs to be,
The cow has to be very thin. The cow?
there are certain brands of ice cream that I will eat and certain ones that I won't. Well,
Wait, I guess you don't eat gluten.
correct. So I am gluten free. So technically, it's a keto slash
Oh, I have.
Grain
Those are
ice
nasty.
cream.
paleo diet.
I tried that. What?
So
It's not like ice cream.
most of the Halo tops I can eat.
I'll get you some berries.
Now there are, if it's like, if it's clean, like there's some Tillamook ice creams that I can eat, which are very basic. You know, it's got cream and sugar, but it's not like corn syrup. So if it's more natural, then that's kind of where we want to go. So, but if it's got colorings that are not natural, like, oh, I love mint ice cream. It just has to be the proper thing. Yeah, so I try to stay away from like the, you know, red number 5 and the blue 40, that sort of thing, because food colorings will mess you up, because they're not natural, they're artificial. Also, the artificial flavorings, you don't know where those things come from.
Skittles.
Okay, you're gonna get
Yeah, so most candies I don't eat now.
Skittles, bro.
The most amount of like candy stuff that I eat is chocolate, and I go dark. Dark chocolate, like the darker the better. Like
Darker the
if it
better.
doesn't have a percentage on it, it's too sweet for me. So, yeah. Yes. When do we leave? 5:30 a.m. January 10th.
5:30 a.m.
Yeah.
Yeah.
It takes 3.5 hours to get there.
And we get back at 11.
Plus, we stop for breakfast.
Oh.
It better be good.
It better be good.
I'm not sure if there's a Chick-fil-A close, but there's a place that we've gone to in the
That's not that
past
bad.
that there's
Not that
like
bad. Did I just hear that come out?
there's
Y'all should go to
Yeah.
there's like
Iowa.
McDonald's, there's a Burger King, there's
Okay,
a Taco Bell,
McDonald's
there's a gas
breakfast.
station.
Taco Bell's
And
always
here in general,
Bell.
like that at 8 a.m.
McDonald's is the only thing I eat from McDonald's.
PB&J for lunch.
Yeah, me too.
They pay for your
So you need to bring your own money for breakfast and for dinner, but lunch is covered by your top.
I mean, it's wild.
Yeah.
I'll just eat my own
Ice
breakfast.
cream cone first.
He was getting from Jordan.
You just want the ice cream.
What?
Not
So
Jordan,
typically,
he-
I'll
number
just
one.
do ice cream
Curtis.
in a cup.
Curtis.
Sometimes I may
I close
splurge
Jordan
for a
number one, Jordan
cone,
number 2.
Well, you know, with if I'm not like allergic to things, then it's a choice. Now, granted, I've been making these choices for the last 8 years, so I'm kind of used to it. And it's not really like a diet in terms of like I'm trying to lose weight, but a diet as in this is the set of foods that I am choosing to eat,
Do you do this?
which is the real definition of a diet.
Do a chicken apple sausage molester.
What's your
So, but yeah, like meat and cheese, I'm all about meats and cheeses. In fact, the key diet is really like high fat, low carb, so that your body changes. And initially, if you want to go keto, it's like a shock to your system at first, because typically a lot of our foods are laced with sugars. Okay. If you look at the label, there's sugar in everything, which is why and there's a whole historical aspect and why that is too, which we can get to later. Yes, yes.
I'm gonna go to France.
Yeah,
Get a
so
French baguette.
I can talk more about how I eat and all that stuff later, but let's get back to
We
this.
just go big.
And regulations are a big no-no.
I could,
At least these are the rise guys.
I could do it on, I'm sorry, what?
Kids, we have diabetes at 12.
Probably not all the
Oh, wait, so.
Somebody hand me the seafood boil. That too. Like potatoes, eggs.
I'm gonna get him a
Yeah.
chicken.
Yeah, that's true.
I'm gonna get him
If he wants fresh, good eggs,
Okay,
you
so
get him a chicken.
let's,
That lays green eggs.
should kind of wrap that up. I will be sending a message out with the wish list as well as all of the possible ideas that if you're looking to do something like that for me, then you got some direction instead of just guessing. So,
We should all pitch
I will
in.
send that out here this week so that you guys, if you choose to, and again, it is completely your choice, to bless me with, some Christmas stuff. But if not, that's completely fine too. I'm not expecting presents at all. So, alright, let's talk about the pendulum.
Oh boy.
Here we go, yes.
Keep on
Oh, boy.
talking. Keep on talking.
It's the North Pole, actually.
You know, it's really cold in here.
It's cold. Do you need another jacket?
Oh my gosh, give her
Now,
the trench
you
coat.
are
Pressure coming from
on
this
the
way.
floor, so it's gonna kind of.
But that seat hurts.
Oh, wait, hold up.
I understand.
Is that?
You can
Are you
sit
sure?
down.
I've seen the wind.
Are you
Let
not
me say this way.
I'm not using it right now.
Wait, that's north.
Yes, go for it.
The
Sit
wind,
right
Technically, it's
Dana,
north.
sometimes I actually think you fall asleep on the floor.
I haven't
Okay, here we go.
fallen asleep yet.
The
Yet.
I'm
pendulum.
just laying there.
So here's the equilibrium. Are you gonna scoot it over, or are you just going to stay there? Okay, cool.
It's right here.
she said, oh,
Alright. Yeah, she did. She just wants to be in the action, you know. Alright, so here's Bob. So Bob's, I'm going to displace him a certain amount, and he's going to start oscillating. So the real question is, does the pendulum exhibit simple harmonic motion? It's going to take a little bit more effort to prove this true, but the end game here is we're looking for an acceleration equation that kind of looks like this, where the omega may be other things that pertain to the pendulum, but it should still work with the whole A equals negative some number times X, okay? So that's the goal. Let's take a look again. We're gonna start off with our Newton's second law. Acceleration is equal to F net divided by the mass. We need to know what forces are acting. Let's take a look at our FBD. So we've got our force of gravity pointing down, and our tension that points up at an angle. We can measure the angle. This would be like if we were at the maximum displacement, we can also measure the maximum angle, okay? Which, with this particular thing, it's really easy because there's a little protractor thingy already set up. Now, we're gonna break it up into its components. Our tension here, so we've got our tension Y and our tension X. And it would be really nice if those Y direction forces were balanced. What motion would be required in order for the forces to be balanced? Not a circular motion, no, no. They have to be unbalanced in order for us to go around in a circle. What has to be true with our motion, think Newton's laws, in order for our forces to be balanced?
Must be at rest.
At rest, or constant velocity. There we go. So, notice that Bob is swinging back and forth, and I can tell that it definitely has some x displacement, some x motion here. Can you tell if it's moving in the y direction?
Yeah.
A little bit.
Maybe a little bit, yeah. Okay. But really, like, if we were to compare, if I just see the x and it's really not moving up and down a whole lot, I'm going to assume, for the sake of this problem, I'm going to assume that the x is really at rest. Okay? I'm going to make that just because I see that the x is doing so much of the motion and there's really not a whole lot of y motion at all. I'm going to assume, okay, assume that our Vy is 0, okay? If that's true, that means that my forces are balanced in the y direction. So that means that my Ty is equal to my Fg. And we all know Fg equals mg. Okay, so knowing that the only acceleration we have is in the x direction, my net force is going to be equal to my Tx, because that's the only x force that we have. Okay, so let's plug that in. So my Tx over m, naturally I need an equation for Tx. I need to substitute in, let's get a relationship. Now I know something about Ty, so if we can pair the Tx and the Ty together, could there be a trig function that contains both opposite and adjacent?
Tangent.
Tangent, yeah, there we go. So let's use tangent. Tangent of the angle is equal to opposite over adjacent. Opposite is going to be my Tx. My adjacent is my Ty. And we're solving for Tx. So Tx is going to be Ty times the tangent of the angle. And remember Ty, because I assumed that it was at rest in the y direction, Ty is really equal to mg. So I'm going to plug that into here. So Tx is equal to mg tangent theta. Cool. So I have an expression. I'm going to substitute into my big equation here. So let's see, mg tangent theta divided by m. The masses cancel. Look at that. And I'm left with this equation. A is equal to g tangent theta. Now, does this look like this? No, not yet. We've still got some work to do. But more importantly, this has a tangent in it. That one doesn't. I got to get rid of that tangent somehow. Okay? And I can't just do the arctangent because it would just go over there and it's a giant mess. So, here's something new, no doubt. Or no cat, I don't know. Probably something new for you. Have you ever heard of the small angle approximation?
No.
Excellent. Okay, so
For what?
here's what it is.
No, yes.
If you have your calculators, break them out. Make sure that you're in radians mode for this. Radians?
Math.
I can show you. Or you can ask your teammate. Small angle approximation. If you've got a TI and a graphing calculator, go to mode. It should be the third option down. If you got a Casio, I gotta look at your specific phone. Alright, hold up. I should fix this.
What does this have to do with it?
It's just, see, I have a family.
It messes with the probably good one, but there's when you solve for like the answer that it messes with. So you have to make sure.
I wish I would have known that yesterday. I took a test yesterday.
You should have had it. Oh yeah.
Not like that one.
Degrees is
Alright, I'm
next,
not
and now we have radians.
So, the cover.
Talk about that anyways.
Oh, You have the same time? Okay, so go to the settings.
D for degree. You want it in radians, so yours is good.
Why'd you do that? Okay, sorry.
This?
No.
Actually, no, this is just, this. You need to charge this. Is it, does it charge or?
So there,
We've been through it all.
there's a
Good,
difference
the bad,
in
the horrible.
like
Watch how Curtis didn't show up because he didn't want to get bullied.
fantasy magic and more like real life type of magic. Well, I mean, the force moving things with your mind. Which again is kind of like a telekinesis, which, you know, like X-Men have that thing too, so I don't have an issue with that. It's just, when you start to bring in real life and spiritual aspects of things, that are, I mean, really, if something happens superhuman, as in outside the natural abilities of being human and what we can do, then it's supernatural. And there's only two places that power can come from. So, and in most cases, if it doesn't bring
That's a little too
glory
close
to
to
God,
my
That's a little bit too close.
it's from the wrong source. So,
Y'all be wanting to go to basics meeting,
yeah.
but then I be going to, I see the message so blank.
Okay, good. All right. So if you're in the calculate mode, so if you go home, you're in the calculate mode. Go to settings, house settings. That's okay. Angle unit.
So you see mode,
Readings.
go to mode, and then you just go down.
And then go back home.
Is
Right. So yours is going to be in your setup.
You want it in degree, you want it in degrees if you're doing like, one of the trig functions, like,
Radians. You're
and you want it in
already
radians
there.
if you're,
So then exit, and then you can calculate.
I'll keep it in radians, but this button is just second.
So it's really not for this actual lesson, it's just the little test that I'm about to show you with the small angle approximation. No. Okay, so, sorry guys, small angle approximation. So try tangent, try doing the tangent of point 1 and tell me what you get with 1 sig fig. You get point 1. I mean, it's the same thing. Try point 2. See what it does.
Oh, it's gonna be point. Oh my god.
It's point 2. Alright, keep trying. Keep going up by point 1 until it's no longer the same.
I'm gonna do 1.
No, you won't. It doesn't take long. Because I know exactly where it changes.
9. I don't know.
Did you just study a calculator?
So the tangent of point 6 is what? Is what? 0.7. Okay, so that's where it stops being the same. So we had this small angle approximation where the tangent of the angle is approximately equal to the angle itself in radians as long as the angle is small. Now, we saw that it got cut off. 0.6 is too big. So can you convert 0.6 radians into degrees for me?
It's 0.6 times 180 over 5.
So you are correct in terms of pi radians is equal to 180 degrees, okay? But make sure that you are putting things in the proper place as we're trying to cancel out. If we're starting with the radians, the pi radians needs to go on the bottom so that the radians cancel, 180 degrees on the top. So how much is that?
It's 34 degrees.
So if 34 is too much, then the small angle approximation is where the angle is less than 34 degrees. can you tell how large of an angle this measures? It goes up to 33 degrees. How very interesting. So as long as I am within this angle range, oops, sorry Bob. My angles are small, which means that I can use this approximation to simplify my equation. So my tangent here becomes just theta. Okay, cool. So we've learned some really cool obscure math stuff for today, but we're not done yet. So this does not look like this, does it?
No.
Because I need an x and I still have a theta. But now technically x would be the distance from the equilibrium to wherever Bob is at that particular point in time.
Correct.
And I could easily measure the length of the string, right? So could there be a relationship that exists between x, what we need, and L and theta, what we have?
Opposite and
Absolutely. What trig function should I be using now?
Cosine.
I should be using sine because I have opposite and I also have my hypotenuse.
Cosine is
So
adjacent
let's go over here. So sine of the angle is equal to opposite over hypotenuse. And opposite is x over my hypotenuse L. But I can't just substitute this because I have sine for theta and I just need theta. I wish that the small angle approximation would work for the sine.
Dang.
Does it?
Probably.
Test it out. Let's see.
Dude, I have a headache.
It does. Damn, what I can do.
I do have a flair for the dramatic. Jazz fingers?
Were you a theater kid?
No, actually, my sister was. But I did spend my time on stage. I was involved in 2 musicals when I was in high school. The first one was a really small role. I was part of the band in The Music Man. And then we did a musical called Sweet Charity. It's actually about a prostitute. Surprised that my parents actually let me take part in that, actually. But I was a chorus member and a dancer for about half of the numbers on stage. So much fun. Best high school experience I had. Yeah, it was so fun.
You go to high
So
school
fun.
in Florida?
Anyway, so does my sine work as well? It does, yeah. So the sine of the angle is approximately equal to the angle itself. Where this actually comes from though, like how in the world did people come up with this thing, okay? It actually comes from the graphs, okay? If you look at a tangent graph, let's do that one first, okay? And you look at small angles, so from 0 to right about here. You look at the graph and it looks like a line. Okay? Same thing with our sine curve. You look at small angles and that graph looks like a line, which is how this is possible. It doesn't work with cosine because the small angles with cosine, it doesn't look like a line because there's a lot of curvature to that. So small angle approximation works with both sine and tangent. As long as we keep our angles under 34 degrees, we are good for this approximation. So that means that the sine of the angle is just equal to the angle itself. And now I can substitute x over L in for the theta right here. And we're almost done with this part. Hey, you guys were asking me all sorts of questions, so.
It was education.
Not really. Yeah, so we're almost there. Look, I've got an x now, and I've got some sort of constants here. So a is equal to g over L times x. The only thing that's missing is the negative. Remember, the negative tells us about the direction, right? And if I'm displacing to the left, remember the acceleration, the direction of that came from the direction of my tx. So if I displaced x, where does my tx point? It points opposite of x. So there should be a negative here. And we have just proven that the pendulum does exhibit simple harmonic motion. It matches up with our master equation here. If we line it up, negative omega squared x, just like we did with our mass on a spring, we can say that our omega squared is equal to g over L. So my omega is equal to the square root of g over L. And I plug it into my period equation. Period is equal to 2 pi over the omega. And we get, eventually, we get 2 pi times the square root of L over g, which was the period of the pendulum equation that we learned about first last class. Comes around full circle. What's up?
Comes around full circle.
Yes.
Alexia,
Very good.
When you, Alexia said
Huh?
that you should have said that. You are a copycat. Earlier, when you said something over there, she told me, she said, be quiet. She said that you should have said it comes around in full circle. And you just said it. So
Look
it
at that.
comes around in full circle.
Yep.
What?
No. It was a lot, and typically, we would take a 5-minute break at this point. But we only have half an hour left in class, and we still got more to talk about. So I'll give you 2 minutes. Okay? I have an answer.
Show y'all a magic.
Talk about it.
I'm gonna take more notes when I get home. I'm not taking any more notes.
Matching up the equation.
My head hurts.
Yeah, so
Look at all
we
that.
were matching up.
You see all the arrows? Like I didn't know where his mind was.
Yeah.
So I kept drawing like arrows over so I could like look back at it. And it makes sense of I need to write like numbers down. Like
Well,
1,
it's
2,
all,
3,
so
4.
both of them are A equals a negative times something times X. And so the somethings, we actually set equal to each other, which is what this is.
You got some food? Sweet.
Yes, I.
Last chance to take a picture of our board before I erase.
Oh, maybe I should do that.
Please tell me I got everything.
That would be a very good idea, isn't it? I will get you. Jordan was that picture, but he's like,
This looked like a dime this morning.
There's quite a bit on the board.
hey, how about like, I don't know, like.
What? Is that a parka?
What is that?
That's a parka.
Okay,
That.
This?
Yeah.
It's comfy.
That's a parka.
It's comfy. Especially when I have to wait for like 20 minutes in the 30-degree weather.
Dude, that's called a sweater.
You,
Let me see it. Is it fluffy on the inside? Dude, this is a,
Yeah, I don't know what
this is a
happened.
parka. I literally have one in my car.
it's comfy.
I was at the wrong end. Spanish
Today's the 3rd. Yep, all day long.
I can give you $1, but not today. I can get you whatever day or selling the beer more boring in the ball. Oh yeah, I do. It's gonna come in a Ziploc bag.
Kayla, if you had that grade that day, that's fine.
It's not a pack.
Yeah.
Is this for a different class? It's like,
Because
it's a regular Ziploc bag.
it's definitely possible bags, because the progress reports, they were finalized, but then, you know, we still keep doing grades. So
Cake call.
if you
And I
said
made
that
it.
you had that grade.
It's not
that
like
day.
I needed to do my quiz too,
I don't like
so I
Lay's.
know my raw grades.
Yeah.
So.
So yes, yes. You are good.
Is this for get you candy?
Whatever you
want to do, bro. They sell so much in there.
About
Sour Skittles.
ball and a cup.
Do they sell regular Skittles or UGC? They do, right?
That was for us.
Oh, for $1, yeah. Okay, okay, you need to tell.
It was, it may not have been your class, but one of my classes, was confused about the wall of death example.
Oh, I get
Okay, while we have a break, can I get some t-shirt sizes from you, Christian?
Medium.
Small, thank you.
Down.
Kayla? Small. Jordan, you sir? Large. Elijah? Thank you.
Actually, it
Sonora's not in this class. Alexia and Alexia. Extra small. And same for your sis? Yeah, that's a choice. Yeah. Extra small for Kayla.
We had AP pre-calc today.
And,
how's your CCMA?
Tyler. You, extra large, okay.
No D's? That's what matters.
All right,
$1.
here we go.
Can I just give you $1? Never do you anything. The one time I plugged this into you, one time.
All right. So I'm gonna hook up a motion sensor to my computer here, and we got a mass on a spring. Hey, there's money. Dana, is this your money? My money? Dana, are you alive?
She gone. Is she good? Stay with
Are
her.
these yours? Would you like them? Careful, your glasses are on the floor. Behind your butt. I have one.
Yeah, he's young child, bro. Young child. Let his brain grow. Alright, man, doing a little too much. All I'm saying is he always gets an A. He's on the A on everything.
Alright, so we're gonna take a look at least the first look about what the position, the velocity, and the acceleration time graphs look like when we have something in simple harmonic motion. We will do more equation stuff with it next class, okay? But this is just a get to know what it actually looks like stuff. So we'll talk about that. We'll talk real quick about phase and the energy changes as a result. All right, so I've got a mass on a spring. The paper is going to help the motion sensor detect the proper motion here. So I'm gonna set it in motion there. Alright, so not perfect, especially with that acceleration graph, but let's see after I auto scale this bad boy. Okay, and I want to start where it's at the maximum displacement, so I'm gonna slide this over just a tad, just right about there, okay? And then I gotta do this one too, skew this one. Yeah, that really is not the best, but that's okay. We are short on time, and we're just gonna work with it. Okay, so what kind of function do you think that top one looks like, which is the position? What's that?
I don't know. Sine? Cosine? I don't know.
It looks like a cosine curve.
Dang it.
Yeah. Yeah. So a cosine curve starts with maximum amplitude. Kind of like that. Okay? And then the velocity, what does that look like?
A cosine.
That looks like a sine, but doesn't the sine start going up and then go down? This one goes down first. A negative sign. Yeah, exactly. So the negative sign, so our velocity time graph looks like a negative sign. I'm going to try to draw these major points here. Like that, okay? And then my acceleration time graph, what does that look like? It looks like another cosine.
It's like brain damage.
But like inverted, like a negative cosine.
Inverse? I don't know.
Okay. So we should know definitely what the forms of these look like. So our position is going to be some sort of cosine as a function of time. There's more to it, which we'll talk about next class, okay? And then the velocity function looks like a negative sine curve. So it's sine, but it's inverted, okay? And then our acceleration looks like a negative cosine curve. Now, remember that our simple harmonic oscillator equation said that our acceleration was always negative of the position. So if the position was a cosine curve, our acceleration should look like a negative cosine curve. It matches, okay? Now, we know that the relationships here, so the slope of the position time graph gives us velocity, and the slope of the velocity time graph gives us acceleration. Anybody in calculus right now? Not pre-calculus, real calculus. Calculus A, no, okay. So eventually you will learn how the derivative in calculus actually helps us find these different equations that are connecting each other, which is super cool when you learn physics with calculus because it really makes a whole lot more sense.
No wonder it doesn't
But
make sense. Right?
that's a whole nother class. Okay, so we need to know for right now that our x and our a should be cosine functions, that our v should be a sine function, and they should be opposite. Notice though what happens. So as we look at the initial states here, both my position and my acceleration are maximum. That's going to be where it's at the amplitude, at the biggest point. But my velocity is 0 at the amplitude, which makes sense because as I pull it back, as I let it go, it starts at rest and then it starts to move, okay? As it starts to move, my position goes down, it approaches the equilibrium point, okay? Until here, where it passes the equilibrium point, my velocity is at a maximum. It's going the fastest as it goes through the equilibrium point. But at the same time, as it's on the equilibrium point, the spring is neither compressed nor stretched. There's no force acting now, so there's no acceleration. But then it passes the equilibrium because it's still moving, right? And as it passes, it recompresses the spring, giving us more amplitude and greater acceleration so that we're here at the other side of the amplitude here, where we've got a maximum x and a maximum a, but our velocity is 0 again, as it slows down to a stop at the amplitude, and then it starts to go back in the other direction. Jordan.
Who's the calculus teacher?
Who's the calculus teacher?
Yeah.
There are several different ones. If you're in IB, it's going to be Mr. Martin. If you're just taking AP Calculus, I believe Mr. Calhoun teaches it. But math teachers are notorious for changing what classes they're teaching from year to year. Okay, it's not like science where I'm only going to teach physics. Like I can't teach chemistry, I can't teach bio, but math teachers, they can float and teach different levels of math based on what the school needs or what they want to do. So just because a particular person is teaching that you don't like, don't let that scare you from taking the class. One, because that's just dumb. But two, they might not even be teaching it next year. Like you don't know what their plans are. They may not even be here at Paxton, okay? Which we don't actually have. Huh?
Do you think you could teach algebra 2?
I have taught Algebra 2 in the past. Technically, it's not on my certificate, so I would be teaching out of field, and you can only do that for 1 year. But I do have the skills to teach Algebra 2, and pre-cal, and calculus, and geometry. The only thing that I don't really have skills for is statistics, because I never took a stat class, because I was always on the calculus route for math stuff.
How many calculus classes have you taken?
Well, in college, there was Calc 1, 2, and 3, and then there was another one called differential equations. Yeah. Which is just more calculus.
Yeah.
So. Yep. Okay, now, let's talk about phase real quick. So phase is when we've got two things that are oscillating, but, and they may or may not have the same frequency, but it's really based on where in the path they are. So like, let's say you and a friend are going to the park and you guys get on swings. And so you both start at the same time, and you both let go, and so you're swinging in sync with each other. That's going to be in phase, because each one of you is hitting your amplitudes and your equilibriums at the same time. Okay, so that's in phase. But if you don't start at the same time, if one person starts before the next, then you're not in phase. Okay? You're not in phase, you're off from each other. Now, you may still have the same period and the same frequency, but the timing is different. In fact, if you look at the sine and cosine curves here, watch my position as I shift it. I can shift it to make it look like a cosine curve. I've changed the phase of the graph, basically. I've changed its timing. So it's still oscillating motion, but really the main difference between a sine and a cosine is really how far it's shifted. It's been shifted a quarter of a period. That's all that the difference is between a sine and a cosine graph. So you might have also seen this, and you will see it next time you go out, but if you watch, like let's say that you're driving, and you're in a turn lane. You have your blinker on because you're trying to turn, right or left, and the car in front of you is also trying to turn, and they have their blinker on as well. In most cases, those blinkers will not blink at the same rate. They will be different, but there will be times, so you'll see them off from each other, but then they'll be in sync. They're in phase, and then they'll get out of phase. And then they'll get in phase again. Same thing happens with wipers, like if it's raining. So you watch your wipers and the wipers of the car in front of you, and when they're exactly opposite, they're exactly out of phase from each other. Okay? But if the rate of the frequency is off, I'm not doing it right. Okay? But eventually they'll be in sync. Then they'll be in phase. But if one is faster than the other, then they'll be out of phase, and then they'll start to be in phase again. So you'll see that also with music, which we'll talk about after a break. great because after oscillations, we jump into waves, which is super cool because we talk about sound and light as well, and lots of cool stuff in the spring. So phase is really just about timings of the oscillations. Last but not least, if you look in your books on page 328, there's some great looking graphs here. The bottom one here, it shows you the changes in the potential and the kinetic energy of the mass on a spring or a pendulum. It doesn't matter. But if you look, if you add the energies together, you always have a constant total amount of energy, which is really equal to the amount of potential energy that I give it initially. As I stretch that spring, that's going to be the total amount that the mass on a spring system has, and when I let go, that total number still stays constant. It just changes from kinetic to potential and back again as it oscillates. But as you can tell, in both the mass on a spring and our pendulum, the amplitude will decrease as time passes. That's called damping, okay? And in this graph on the top of page 329, we have a damped oscillation, excuse my French, so that it tracks that the amplitude due to frictional forces, either within the air itself or some other like spring internal friction here, but the amplitude will decrease, the period stays the same, the frequency stays the same, so it's not slowing down its rate of oscillation, it's just not going as far each time. The amplitude has decreased, and therefore the energy will decrease as well. If you track the tops of this graph, that's actually an exponential decay function. So it's going to go down and down and down. Eventually it's going to get to 0, but it's going to take a long time. I mean, technically it's never going to reach 0 because things are always oscillating, but you would have to look at the atomic level to see that. And we're just looking at it macroscopically, so it shouldn't matter. But yeah, so cool stuff. All right, I think I'm done. Yeah. So your pods are proper for on the homework schedule. Proper, I don't know why I know that. So feel free to use the rest of class time, or I know it's been a long lesson with other talking in there as well.
Just a little bit.
So feel free to jump on the pods. The quiz is up already. We have one more lesson. Last lesson on Thursday, last lesson of the second 9 weeks. So come prepared.